Hello, good morning. Of course, good afternoon. So today we will discuss something about the synchronous counters. Synchronous counter is a very important counter. It is not the straightforward counter to be designed. The design of synchronous counter could be in backward, a bottom to up approach. Okay, so it could be a bottom to up approach. How this could be? You are not supposed to directly draw the circuit diagram for synchronous counter here. So you need to do many mathematical, let me say, Boolean calculations while doing this particular design of a synchronous counter here. Obviously, we have observed in the previous classes, we have observed many items here. Let me show you. Wait for a while. I'll come to that particular point here. Okay, registers it is over. Okay, shift registers it is over. Yeah, you can see synchronous counter and asynchronous counter here. We have taken these two, a ripple counter and a synchronous counter. Two different types of counters have been taken into consideration. As usual, so here you need to understand synchronous counter will be taken, so need to understand one particular point here. So the synchronous counter could be taken common clock pulse, that is a common clock pulse, and it could be triggered for common clock pulse which have been connected to all flip-flops. So will be available within the design of the synchronous counter. Synchronous in the sense everything will be shared same kind of common clock pulse. That is called as synchronous. Okay. So here also we would like to discuss the same here. So let us consider the same point will be repeated here also. The synchronous counter would be taken common clock input for all inputs to receive the common clock pulse here. And moreover, when a common clock pulse are here also, you need to remember when a pulse will be generated something like this. So when so it is being one, it could be. So when this particular let me take another color. So when so it could be 0. So from here to here, it could be considered as 1, and it is being negatively triggered at this particular position. It has been negatively triggered, and it will becomes to complete 0, and then again positively triggered. So you could consider this is a positive trigger, and it will continue for some particular time, and afterwards it will be again negatively triggered. After negative trigger, it will be reached to 0 and continue for some amount of time. This amount of time is a discrete amount of time. So delta t will be always common for, so delta t between these two and delta t between these two, delta t between these two is common. Everything is common. Though we may be write this one with a small, distances will be somewhat a little and bigger in between these two. There is no problem. But as far as the distance between these two will be always common. So it is, first of all, it is negative to positively triggered and will continue sometime, and then negative triggered and will continue sometime here. You need to understand this particular point here. So when it could be positively triggered, then the clock pulse will be generated, its pulse, and it will be so supplied to all flip-flops which are available within the design of our counter. Previously, what we did, so previously, if you consider this is the clock pulse and so on and so forth. So when negative trigger will be there, when it could be reached to 0, then the flip-flop will be external, first and foremost, the flip-flop can be taken input, and it could be generated some output. Based on the output, second flip-flop will be so responded. Based on the response of second flip-flop, third will be responded. So and so on and so forth. Previously in a ripple counter or asynchronous counter. But here, synchronous counter, the basic point you need to remember, so common clock will be connected to all flip-flops. Okay, to all flip-flops it is connected. So here you need to understand. So this could be considered as a common clock pulse, and this common clock pulse will be taken in such this like this. This pulse will be connected to all flip flops. How many number of flip flops are there in our so counter? Everything has been connected. This one. Then when it could be, I mean, flip flops will be generate its or transferred its value from 0 to 1 or 1 to 0. When it could be done here in the sense when it is positive triggering. Okay, from 0 to it will be turned to positive and will continue some amount of time up to this particular point. It is called as 1 here, and as and when the time is gets over, then it will be moved to negative triggering. After reaching some amount of time, it will continue with 0 for some amount of time. After this one, again positive triggering. Now it could be reacts at this particular place. So clock will be generated at this particular places here. In this way, so the clock will be taken. Now this could be considered as a negative. So downward direction will be called as a negative, whereas upward direction will be called as positive. Okay, that is what you need to. The common clock triggers all flip-flops simultaneously. What does it means? Triggering, when we have to consider the triggering, what you need to understand, whether it is a positive direction or it is a negative direction. Okay, based on the construction of your flip-flop, it might be either it is a positive direction or it is negative direction. Synchronous counter will be always triggers during its positive direction, I mean 0 to 1, whereas asynchronous will be triggered towards a negative direction, that is, I mean negative edge triggering, that is 1 to 0. When it will becomes to 1 to 0, so asynchronous will be gets worked out here. So that is what you need to understand very clearly while going to start this synchronous or asynchronous so counters here. Then followed by there are certain number of steps to be followed to construct this synchronous or synchronous counter here. So let us consider to design so this synchronous counter. We need to follow some number of steps here. Totally 4 or 5 steps are supposed to be followed here. First step is identify how many number of bit so synchronous counter is being implemented. For example, I wanted to implement, so the counter will be counts right away from 0 to so 15. For example, let me consider, wanted to implement this particular counter. How many number of bits are required here? 15 will be represented in binary 1, 1, 1, 1. So therefore, 4 so bits are required here. For example, I'd like to implement, so let me consider 0 to so 1023. Up to this particular value, I would like to implement. So how could you write this 1023 here in the sense 1023 will be written by taking so 10 bits into consideration. Okay, so continuously 10 ones will be written. If you calculate 10 ones, so then the 10 ones equivalent value is 1023. Of course, totally it is 1024. 2 power n minus 1. That is the meaning here. So 10 bits are required to implement this kind of a counter. So therefore, you need to identify how many number of bits will be required to implement one particular counter. And if you want to generate, or if you want to construct 4-bit counter, so you also need to identify how many number of flip-flops are required. For each and every bit, one flip-flop is required here. One flip-flop can be required here. So if you want to implement 4 bits, 4 flip-flops are required. If you implement 3 bits, I mean up to 7, 3 flip-flops are required. If you are implement up to 1023, so it may be required. So 1010 flip-flops are required. Okay. So in this way, so we would like to identify with the first step. And second step, what is the second step here? After identifying how many number of bits are required by you, then you have to write Using which flip-flop you are trying to, apply, so that particular flip-flop also taken into consideration. So based on the flip-flops what you are supposed to implement the synchronous counter, so you need to write its truth table must be so taken into consideration, and at the same time excitation table also be taken into consideration. Let me give you what is excitation table today. Okay, so you never come across this excitation table so far. I'll give you today. Now, then followed by, after this one, after taking so excitation table and after taking all these, then what is the next step you are supposed to do here is, so what is the next step you are supposed to do is, so determine so which flip-flop, I mean determine so flip-flops inputs must be presented inputs must be presented for desired next state from the present state using excitation table. So E has been missed here, STATE. Okay, E has been missed here. However, so you need to identify what is the next state of the flip-flop based on the present states. And these next state values will be identified based on the present states in excitation table, not from the truth table, excitation table. Okay, so you need to identify this particular point will be considered as third point. And the fourth point will be, after considering so next positions or next state values, each and every state, each and every flip-flop. For example, if you are trying to implement by using JK and wanted to implement a 3-bit counter here, so first flip-flop JK, J0 and K0 will be there. Second flip-flop JK, so J1 and K1 will be there. Third flip-flop, J2 and K2 will be there with you. So these many flip-flops are available here, and all these flip-flops are going to be connected in a particular way. Okay, we will see at the end. So in a way, you could get some kind of counting facility here. However, you need to identify, so whatever the excitation table you have to take into consideration from those. So draw the Karna map and identify the value of J0. Again, draw the Karna map and identify the value of K0, and so on and so forth. If you are trying to implement a 3-bit counter, 1, 2, 3, 4, 5, 6 K maps will be required for you. So all these 6 K maps will be identified. So the values of J0, so K0, this is one set first flip-flop inputs. You need to identify inputs of first flip-flop and how these will be connected. You need to take the connections, why this will be taken into consideration, and then followed by how J1 and K1 will be connected each other, and how J2 and K2 will be connected each other. You need to identify what is the interconnection between these three by using K maps. So finally, what is the conclusion of this step is, you need to draw 6, for example, 3-bit counter, synchronous counter will be implemented by you. So 3 into 2, 3-bit synchronous counter will be implemented using JK. For example, JK, for JK, 2 inputs might be there, 3 into 2, totally 6 K maps must be drawn by you. From the K map, you may be obtain what are the values of J0, K0, and J1, K1 in the second flip-flop, J2, K2 in the third flip-flop. Based on that, circuit diagram will be drawn. Based on that, finally, so fifth step, circuit diagram will be drawn based on the inputs which have been available with you. So after identifying so-called K maps in this particular synchronous counters. So these must be taken into consideration while you have to implement synchronous counters. What you do? Identify how many number of bit counter will be taken into consideration, and so how many flip-flops will be required, and what kind of flip-flop you are supposed to use. Okay, first of all, number of bits, how many bits are required by you, so required to implement the synchronous counter, and the type of the flip-flop, so type of flip-flop FF, and then followed by after this one, so how many number of flip-flops will be available, needed, how many number of flip-flops will be needed. These 3 points will be taken into consideration of number one. Number two, so based on the type of flip-flop, you need to draw truth table and excitation table. Okay, excitation table and truth tables must be drawn by you. After this one, what shall we have to do? So for each and every flip-flop, so we do have two outputs. One output is a present state output, and the second output is the next state output. So what we did, or what we learned in the flip-flop point of view in the previous classes. So based on that, what is the desired next state? What is the desired next state? It must be identified based on the present state using excitation table, not truth table, excitation table. You need to take into consideration. After that, for every input of a flip-flop, you need to draw Karna map, and required value could be deduced from the Karna maps. After getting the, after the deduction of this deduction of so inputs of K-maps, then you need to draw the logic diagram finally. So this is the total number of so steps we need to follow so to implement a synchronous counter. So let us go ahead with the first step. So step number one will be identify. So here we are trying to specify with so JK 3-bit so synchronous counter, because 3-bit synchronous counter will be taken 6 different K-map simplifications. So that let us go ahead and discuss about only 3-bit at this moment. So 3-bit so synchronous counter will be taken into consideration. So therefore, because of so 3-bit, we need to 3-bit 3 bits are required, and JK, by using JK flip-flops, we are trying to implement the synchronous counters here. So therefore, 3 JK flip-flops are required for construction of this particular so synchronous counter here. Number 2, this is the first step. Number 2, it's very crucial. Second step is crucial. Third step, fourth step, fifth step, of course, these are very easy. So it is very, very crucial to be understand. Look at this. So the truth tables and the excitation tables must be drawn by you. So truth table, we know very well. So if 0, 0 will be submitted, so whatever the previous value, q n plus 1 will be next state. So if 0, 0 will be there, whatever the previous output, the same output will be continued. If it is 0, so 0 will be taken for next state also. If it is 1, so for example, it could be previously it has been 0, 0 will be continued as next state. So Qn will be equal to, so 0 in the sense, so Qn plus 1 also, so n plus 1 also will be equal to 0. And if it is 1, so Qn, for example, if it is 1, there is no change, next state also 1. So that is the meaning of no change. So J will be equal to 0 and K will be equal to 1. So based on the activity of JK flip-flop, so you could get irrespective of a previous input or previous state, so it has been set to 0. So that is called as, it is called as reset value. And J will be equal to 1 and K will be equal to 1. So irrespective of the previous state, it must be set to 1. So this state is called as set state. And J equal to 1 and K equal to 1, whatever the input, whatever the previous state it might be, that state must be complemented. For example, previous state is 0, so next state must be 1. Previous state is 1, next state must be 0. So that is why it is being generated complementary form of previous state. So that is why it is called as toggle form. Already we have seen everything in the previous classes. It is well known. Then what do you mean by excitation table? What do you mean by excitation table? Excitation table will be always generated. I have present state with me. I have present state with me. And I would like to consider this is my next state. This is my next state. If you consider in such a way, what could be the inputs of J and K here? What could be the inputs of J and K here? I hope that you understand. I have a present state with me. I am guessing next state will be this one. Qn plus will be the next state. If present state and next states will be there with me, something like this, then what will be the possible values of J and K as inputs? That is what the excitation table. Previously, what you are supposed to do, J will be taken some input and K will be taken some input, so that we have to evaluate the flip-flop activity. Okay, Q and Qn and Qn plus 1 are two outputs actually. Qn is a present state output and Qn plus 1 is a next state output. So that is actually formal way of evaluation of flip-flop. But here excitation table will be always illustrate you or so gives you, I have a present state of this one and I have a next state which is guessed by me, something like this. Then what are the possible inputs you have with you? So, okay, so that is the point you need to remember here. For example, two inputs are there here, whatever the names it might be, two inputs are there. You have possible will be 0, 0 is one combination, 0, 1 is another combination, 1, 0 is another combination, 1, 1 will be another combination. Okay, these are the combinations. So now, so what are the possible inputs? Now my present state is 0, my present state is 0. I am trying to get the next state as 0. So next state as whatever the present state, same state will be so generated here. So if it is possible, how the excitation table will be. So my present state is 0 and excitation state will be, sorry, next state will be 0. How it could be get? Look at this, present state is this one. So sorry, next state is this one as per the truth table. So what are the inputs of J and K? So J and K inputs might be, J will be equal to 0 and K will be equal to 1. If you take this J equal to 0 and K equal to 1, so next state will be gets n, 0. Look at this particular place. Now, one more point also be discussed here. That point is, if you are supposed to submit 0, 0, if you are supposed to submit 0, 0, what is the previous state here? That is 0. What is the next state? Also 0. So what do you mean by 0, 0? J and K inputs are 0, 0. There is no change. Whatever the previous state, that will be continued as next state. Okay, there are two possibilities. Possibility number one is, if you send J equal to 0 and K equal to 0, you may be get the next state as output of 0 here. Otherwise, if you send 0, 0, it's also be get the same kind of output. Okay, two possibilities are there. Hope that you understand. There are two possibilities are there to get the output of next state output as 0. First one is straightforward. The straightforward one is, if you have 0 and 1, next state output is 0. Okay, 0 and 1, you get the next state of output is 0 here. This is next state. And second possibility, present state is 0. It is wants to continue the same in the next state also. There is another possibility here, that is 0, 0. If J and K values will be equal to 0, Qn will be continued for Qn plus 1 as well. There is no change in the previous output. So therefore, these are the two possibilities you get. Second thing, so 0 and 1. Presently, I have 0 with me as Qn, and I wanted to get in the next state, I wanted to get 1 here. What are the possible inputs of J and K here? Look at this straight away. We have one particular set of values which are from this particular truth table, that is 1, 0. So if you send 1, 0, you could get so present state will be 0, that will be taken as 1 here. And one more present state will be 0 and the next state will be its complementary form. So there is one particular state, one more extra state will be there with us. If both will be equal to 1, whatever the present state you are having, that will be complemented. Okay. So because of this reason, you could have these two. Oh, sorry. You could have these two. I'm unable to draw the line in a proper way. So however, so you could have this particular, these two particular So states where exactly you could get, if your present state will be 0 and wanted to get next state as 1. So if you send 1 0, you could get, or if you send 1 1, you could get. Okay. Now, thirdly, present state is 1. So if you take what kind of inputs might be taken by J and K, you could get 0. Straight away, you have one input here. So next state will be 0. You could see this is the specification. If J equal to 0 and K equal to 1, J equal to 0 and K equal to 1, straight away 1 to 0 will be come across. And second thing, present input is 1 and the coming next state input is, present output is 1 and the next state output is 0. So 1 to 0, that means complementary form of 1 has been taken. So therefore, the complementary toggle state will be taken by 1 1. When J equal to 1 and K equal to 1, you could get toggle state. So therefore, so these are the two possible conditions where exactly you could get. So the present state of value could be transmitted to 0 here. Okay. Then followed by 1 1. Present state is 1 and next state could also be 1 here. So if you want to get such kind of output, what are the values you have with you to evaluate? So next state will also be 1 here. So look at this. So next state will be equal to 1 in the sense this is the state where exactly you could get. So one possibility will be if you send the 1 0 to the JK flip flops, then you could get so next state as 1 to 1 here, and the present state is 1 and next state also be 1. So there is no change at all. So for this particular reason, we have one more point of view, that is 0 0. If you take 0 0, whatever the QN value that will be continued, so it is one more kind of input. So look at this. These are the possibilities. Hope that you understood what I spoke to you just before. And you need to take into consideration J and K. So look at this. Wanted to 0 0, for example, wanted to 0 0 and wanted to 0 1, wanted to 1 0, wanted to 1 1. If you want to specify something like that, so then what kind of our inputs might be? So look at this. In these two cases, so J will be common, that is 0. J will be 0, but K will be either 1 or 0. So if you wanted to produce either 1 or 0, that condition is called as don't care condition. Okay, don't care condition, any one of them. So either 0 could be produced or 1 could be produced. And here, if you observe this one, here in second case, if you observe this one, J will be 1 and K will be 0 or 1. So this is called as, again, don't care condition. And here, so it is from 0 to 1, which is called as a don't care condition, but K value is equal to commonly available, that is 1. And if you observe this one, J will be 1 to 0, J will be 1 to 0. So, so therefore it is called as don't care. So K will be common value, that is 0. So finally, this is what the excitation table will be. This is what the excitation table will be. So these are the inputs for getting these outputs here. This is what about excitation table. I have already drawn. For explanation point of view, I have written on this particular area. Let me erase everything. Then I will show you how the things will be happening here. Let me erase. Okay. So look at this. So hope that you understood what I spoke to you at this moment. Otherwise, you will go through this video one more time after. So given this link, YouTube link to you people. Look at this. So these are the okay. These are the inputs. So 0 0 as inputs, 0 1 1 0 1 1. So from right now state to 0 to 0 will be gets continue in the sense one possibility will be 0 1. Look at this, 0 1 will be taken into consideration. If 0 1 will be supplied by you, 0 1 will be supplied by you, then obviously, then obviously you could get yes, you could get So next state value as 0, that is 0, 1. If you produce this one, so 0 will be get occurred. Otherwise, whatever the previous state value, that must be continued. That is the question here in the sense, then there is no change kind of state will be there with us. You could also pass this to. In this way, you have to get the values in such a fashion here. So therefore, they will be considered as like this. They will be considered as like this. So just before I have given complete explanation to you people. And if you precise this particular complete explanation into, so 4 by 4 matrix, something like this, it could be seems like this. 0, 0. So Qn, present state and the next state will be, both will be equal to 0. So J must be equal to 0. K might be either 0 or 1. Either 0 or 1. You may be produce either 0 or 1. 1, 0, 1. Present state will be equal to 0 and the next state will be 1. If this is the case, J must be equal to 1 and K will be either 0 or 1 here. K might be. So 1, 0, J must be either, J may be either 0 or 1, but K must be 1. So this is called as excitation table of the JK flip-flop. I hope that you understood what I spoke to you at this moment. Okay, so now what exactly we are supposed to do in the step pointer. So here excitation table has been drawn by us. Now we need to draw so K maps of different kinds of values of I mean different kinds of inputs of each and every state so flip flop here. So it would be take huge amount of time. So right now, so we have completed almost all 35 seconds. Sorry, 35 minutes. So it could be very easy to explain, but will be taken huge amount of time here. So for that particular point, so here you need to fill up all these values. So these values must be filled here. Let me explain everything and how you could get these values. Let me explain and how you can get these values. So this must be explained and how these values must be get. All these things must be explained to you. Will be take a huge amount of time. So we have only 5 minutes of time with me. So it is not possible to explain this particular, I mean, this huge amount of, filling of values from the excitation table so that, so we will discuss the point by tomorrow. We will complete the explanation for synchronous counter. Of course, we will discuss this particular point and the Karna maps will be drawn by us by tomorrow and logic diagram also drawn by us by tomorrow. So this is what the class for today. Okay.